Good afternoon. I'm Zhaohua Wang from the Institute of Computing Technology, Chinese Academy of Sciences. Today, I would like to present my paper, Exploring the Eastern Frontier, a first look at mobile app tracking in China. My presentation will cover the following aspects: the motivation, data set, and methodology, our three key findings, and the conclusion. To begin with, why is it necessary to study mobile app tracking in China? In recent years, the tremendous development of smart devices and mobile network services has stimulated the popularity of mobile apps. Cisco projected that by 2022, the monthly global mobile data traffic will be 77 exabytes. Many mobile apps are bundled with mobile advertising and tracking services, namely ATS, such as the Google Ads. They are used for various purposes such as app maintenance and user understanding. However, this can result in such apps exposing rich and sensitive user data to ATS services, and such tracking behavior often cannot be controlled by users, particularly after granting apps permissions. All of this raises great concerns for protecting users' privacy. Due to the importance of this topic, there has been a large body of research in this area, but they near exclusively focus on Western countries, primarily in North America and Europe. China, as one of the fastest growing countries in mobile data traffic, it has unique local regulations and network policies. Many Western services like the Google, Facebook are not accessible in China. However, China's tracking market is poorly understood, and we have little evidence about how existing findings may generalize to the Chinese market. So, in this paper, we focus on address this deficiency. Next, I will introduce our dataset and the methodology for characterizing mobile tracking in China. Our dataset contains user access logs collected from a major 4G ISP. The access logs are generated by combining the traces of DPI deployed at serving gateway and the information provided by the mobility management entity. Each log corresponds to an HTTP request and contains the following major fields: the anonymized user ID, destination IP address, request URL, HTTP referrer, the user agent, data volume, and a timestamp. Besides, the DPI appliances identify the mobile apps which generate each HTTP request. In total, the dataset contains about 2.8 billion logs of about 3.5 million users in a major city of China. And we identify 1812 mobile apps, with 12% of logs remain unattributed. For ethical issues, when users subscribe to the ASP.NET log, they are informed that their personal and access information may be collected and shared for research purposes after anonymization. The dataset is kept in the ASP's data center, and we have been granted with access in the request URL, HTTP referrer, and user agent fields. To identify ATS domains in our dataset, we utilize 4 ATS-specific lists provided by the AdBlock Plus and HTTP-CAS. They are commonly used by ad blockers. Note that we also incorporate the Easy List China, given that we target China's internet. These lists contain a set of string matching rules. We apply the rules to both the URL and HTTP referrer of each flow. Finally, we attribute 9.2% of HTTP requests to ATS domains. This covers 24,985 fully qualified domains and 8,773 second-level domains. Next, we identify the trackers that are used by individual mobile apps. Note that to simplify analysis, we only focus on the top 500 apps that account for 99% of traffic. Here, we utilize a heuristic approach based on the intuition that trackers requests should happen at a time close to the app's access, assuming it's less than 1 second. Thus, we can associate an ATS request to the closest app's request that precedes it. But a problem here is the possible effect of the background traffic from other mobile apps and the periodic requests issued by some trackers. To mitigate this influence of background traffic from other apps, we divide the user's request into sessions. A session can respond to a set of user activities before an obvious pause. Here, we set the session interval to 1 minute. Next, we filter out the sessions that contain requests from more than one app. For the remaining sessions that contains only one app's request, we can safely obtain a number of candidate ATS to app matching pairs. We further mitigate another effect related to the periodic requests from some trackers. Given that this happens only occasionally, for each app, we filter out the matching trackers that are seen by a few people, that is below the average number of records. Finally, based on the inferred ATS domains of each app, we process all the access logs for each user to associate the ATS request with its host app. Additionally, it's important to highlight potential limitations in our data. First, the 4 ATS lists used for identifying ATS domains may not fully cover the current mobile trackers in China, but we have identified a number of prominent and recognized mobile tracker domains, which are in line with the Chinese mobile ecosystem. Besides, the heuristic method for the ATS to app association may not fully capture the up-to-date trackers of individual mobile apps. We manually test the existing ATS domains for the top 10 most popular apps and observe the association accuracy of F1 score is 0.75. Based on the above data, we can now give insight into the mobile tracking patterns. The first question is, how prevalent are mobile trackers in China? To answer this question, we first model the domains accessed within an app as a bipartite graph G. In graph G, vertices in U denote mobile apps and those in V represent the ATS domains, colored in blue, and the normal visited domains, colored in orange. This graph reveals connections between trackers and mobile apps. With this graph, we make the following observations about the presence of ATS services. Within each app, the median number of ATS domains is 6 for fully qualified domains, confirm that they are widely used by mobile apps. We also inspect the cross-app tracking behavior, with over 30% of ATS domains appearing at least 2 apps, which is much more than the normal app domains. Furthermore, we analyze the top 20 most popular ATS domains as shown in this table. Notably, China's tracking ecosystem is dominated by key domestic trackers. The top 6 trackers are all Chinese trackers, and they are accessed by over a quarter of all apps. In contrast, foreign trackers such as the Google Analytics.com and Flurry.com make up the minority of ATS traffic. They are used by under 20% of apps. Many factors, including the internet censorship, language, and the unique local regulations, contribute to this unique ecosystem that differs greatly from the Western countries. Next, we want to understand which apps are responsible for utilizing this wide range of tracking services. To this end, we group the mobile apps into 23 categories based on their functionalities. Then, we count the number of trackers per app and present its box plot distribution across different app categories in this figure. Each box is ranked in descending order by the median value. The results show that trackers tend to be active in some app categories. For example, input methods have the most trackers per app. That is particularly worrying, as they have incentives to log and collect user input to improve their services. Besides, the communication has the highest mean value of 16 ATS services per app, and the top 5% of news apps use over 26 ATS services. In the above analysis, we know about the mobile trackers usually appear on as many apps as possible to enable cross-tracking of users. This may lead to implicit connections between trackers to mobile apps. Thus, the second question is, what's the community structure of ATS? Based on the two-mode graph G mentioned before, we first create a one-mode ATS projection graph from the largest connected component in graph G. In this new graph, the vertices only contain the ATS domains, and the edges are created if any two vertices share a common neighbor app in G. This graph captures a collocation of multiple tracking services used within individual apps. In this graph, we use the degree centrality to measure how likely a tracker tends to collocate with others. Accordingly, we can clearly identify two types of trackers: the popular ones with a normalized degree centrality over 0.2, and the raised or non-popular ones that sparsely connect with others. Indeed, the popular trackers are present more pervasively among apps. We further measure the degree to which trackers tend to cluster together. It's shown that the global clustering coefficient of the whole graph is relatively high, but the coefficients for popular trackers are much lower than the non-popular ones. These results imply that the graph is very well connected, where the non-popular trackers form local communities, while the popular trackers are densely connected with the non-popular ones. To verify this conjecture, we also apply the community detection on the subgraph that only consists of non-popular trackers. Finally, we discovered 10 communities and 46 isolated components. We next examine the popular trackers to see whether they are collocating in the same apps with each other. To this end, we use the Jacquard similarity coefficient to quantify how likely two popular trackers are to co-occur within the same target app. As this figure shows, the top popular trackers such as QQ.com, Yumeng.com, and 71.am tend to co-occur with each other. Their holding companies are Tencent, Alibaba, and Baidu, respectively. These three Chinese tech giants generally offer complementary and competitive services. In the above analysis, non-popular trackers form a number of local communities. This leads us to explore the specialization of non-popular trackers. That is, whether a local community of trackers intends to occur in some specific app categories. To this end, we compute the tracker specialization index for each local community of non-popular trackers. The TSI measures the extent to which an ATS local community is dedicated to a certain app category. The results in this figure reveal that non-popular ATS local communities tend to be specialized in only one or two app categories, and we observe that they provide specialized tracking services relevant to particular apps. For instance, the education apps are mostly tracked by some ATS local communities run by the companies providing educational-related services. The last question I care about is, how are users impacted by ATS services? First, the heavy-tailed distribution of ATS popularity leads us to conjecture that some may have a monopoly on certain users' data. Here, we utilize two metrics to test this. They are the user tracking potential, namely UTP, and the tracking monopoly index, namely the TMI. The UTP measures the fraction of users that a tracker can track, and TMI measures the extent to which a tracker reaches users that others do not have. For example, assuming there are 3 trackers and 7 users, the tracker number 1 and number 2 can reach more users than tracker number 3, so they have a larger UTP. However, since the tracker number 3 reaches users that the other 2 trackers do not have, so its TMI is equal to the maximum one. Overall, a high TMI indicates that some users are exclusively reached by the tracker, and may be due to tracker's high prevalence and specific coverage on mobile users. By testing the UTP and the TMI metrics of the top 30 trackers, we observe a high penetration of the tech giants in China. For example, QQ.com holds both high popularity and high tracking monopoly, but for 71.am, UC.cn, and 360.cn, although they only track under 20% of users, they have relatively a high TMI. Regardless of privacy implications, the data sent to trackers leads to increased resource usage. So we are next curious to see what volume of users' app traffic is generated by trackers. We observe that 5% of users send over 10% of app traffic to trackers. And taking the OS for consideration, we found that iOS users tend to send less data to trackers than Android users. We next proceed to explore if any personally identifiable information, namely the PII, is uploaded to mobile trackers. To this end, we process each URL in our dataset and use regular expressions to detect the common UIDs on mobile devices, including the IMSI, IMEI, the SIM number, the MAC address, and the advertising ID. Our analysis reveals a varying volume of PII leakage. As many as 10% of users send their PII to trackers via their mobile apps. This figure shows the distribution of how several popular trackers receive PII from apps. It's shown that the IMEI, IMSI, and MAC address are equally likely to be collected by trackers. A particular concern is whether PII is sent across borders to other countries or regions. We found that more than 90% of PII tracking flows are inside mainland China. This may be largely driven by the predominance of Chinese trackers and the blocking of several key US trackers such as Google or Facebook, and this may also be due to the extensive support for HTTPS in the majority of Western countries, but which is not included in our analysis. In summary, we provide the first study on China's mobile app tracking from a 4G cellular network. Firstly, we observe a distinctive mobile tracking market that is dominated by several top popular domestic trackers. Secondly, we discover a very well-connected tracking community where the non-popular trackers form many local communities, with each community tracking a particular category of mobile apps. So last but not least, we found that 10% of users upload their PII data to trackers, but most of those PII tracking flows are confined to China. To sum up, we hope our findings can inform users and stakeholders on the interplay between mobile tracking and potential security and privacy issues. Thank you very much. Any question?